Hello. So in today's lesson, we will delve more on the Gaussian elimination applied for general systems of M equations and N unknowns. So I think I mentioned a couple of times in the previous lectures that the elimination method, this Gaussian elimination that we learned based on the augmented matrix, doesn't require a specific number of equations and unknowns, which is one of the great things about the method, or the algorithm if you want. You simply don't care to begin with how many equations and unknowns you have. If you proceed with the algorithm and you know what you're doing at each step and you know how to interpret the result, then basically you can solve any linear system with any number of equations and unknowns. And as I mentioned before, there are essentially three possibilities. Either you have a unique solution, infinitely many solutions, or no solutions, or in other words, an inconsistent system. So it might be worthwhile to, again, have that formula sheet with the Gaussian elimination in front of you. But just to give you a refresher, the goal is to take the augmented matrix in the so-called row echelon form, or REF, which roughly speaking is described by the following properties. The leftmost non-zero entry on each row should be 1. This is also called the leading one or pivot. Pivot is used in a slightly different, not slightly, but in a different context in which we use row operations in the row echelon form, but for a completely different type of problem. So you can call it leading one or pivot, that's fine. And I will call that one often this way, leading one or pivot. So the first non-zero entry should be 1. Then the other property is that there are 0 entries below each leading one. And notice that it's not arbitrary that I put this on the second position when I describe this row echelon form, because this is kind of the order of producing this row echelon form. You move from top to bottom, and once you establish the leading one, you produce with row operations zeros underneath. The leading ones are shifted to the right, and they will be automatically shifted to the right if you proceed from top to bottom. And then if any 0 rows appear, they should be at the bottom of the matrix, which means sometimes you may have to do interchanges of the rows to accomplish that. Now, there is another more even simpler form for the augmented matrix, which is called the reduced row echelon form. Or RREF, which is essentially a matrix in the row echelon form. So one must bring the matrix in this form first, but then you produce extra zeros. So in addition to that, there are zeros above leading ones. And they are produced, let's put that in parentheses, they are produced from bottom up using row operations. All of this will make more sense once you see the example. This is one of those topics in math in which the example shows far more than the description in the words or what we're talking about. So to move from row echelon form to reduced row echelon form, you basically do the same, you're going to do the same type of operations, but in reverse. Starting with the bottom row, you start with the leading one of the bottom row, you produce zeros above it, so that in the row reduced echelon form, columns with leading ones contain only 0 entries, except the leading one, of course. So except the leading one, all other entries are 0. So let's suppose that you are already with the augmented matrix in the row echelon form. So let's say the matrix is 1 minus 2, 1. And if this is an augmented matrix, then you have the vertical bar signifying the equal sign of the system. 0, 1, 2, 3, let's say that's the second row, and 0, 0, 1, 1, the last row. So this will be a system of 3 equations and 3 unknowns, right? So I mean, the columns would correspond to 3 variables, x, y, and z. if you were to solve, so this is in row echelon form, if you were to solve the system right now, rewriting the equations will give you x minus 2y plus z equals 1, y plus 2z equals 3, and then z equals 1. And then you do the back substitutions, y plus 2 times 1 equals 3, that gives me y equals 1, 3 minus 2. Go back to the first equation, x minus 2 times 1 plus 1 equals 1. 1 cancels, move 2 over, that gives me x equals 2. So that is one option to stop at the row echelon form and solve the system. But you could proceed further to the simpler form, which I called, again, reduced row echelon form, and make zeros above the leading ones. So these are the leading ones that I'm emphasizing right now. How do you produce zeros above them? You start with the bottom row and produce zeros above leading ones. So I'm going to do first zeros above the leading one of the third row. So using the third row, which from now on doesn't change, I'm going to produce zeros above it using the third row. So and also on the first row as well. So I'm going to produce zeros instead of 2 and 1 on the last column. So how do I accomplish that? Well, row 2 becomes the old row 2 plus minus 2 row 3. And row 1 becomes the old row 1 plus minus 1 row 3. And row 3 will stay the same. So the reversed process, which is the reason why, to emphasize the way you do this work, I'm going to start with the bottom row, because the bottom row now doesn't change. It remains 0, 0, 1. And let's follow the row operation now. Minus 2 times row 1. And because already we have zeros, you see the computation is kind of easier right now. So minus 2 times 0 plus 0, that's still 0. So all the existing zeros are not affected. 0 times minus 2 plus 1, that remains 1. Leading ones are also unaffected. 1 times minus 2 plus 2, that makes it 0. 1 times minus 2 plus 3, that makes it 1. Now the first row, we do minus 1 times row 3 plus row 1, minus 1 times 0 plus 1, minus 0 times, minus 1 times 0 plus minus 2, that's minus 2. And then finally, minus 1 times 1 plus 1, that's 0. Minus 1 times 1 plus 1, that's also 0. Pause if you want to catch up and make sure you do the computation on your own. Don't just watch this. I mean, it's very important to pause and actually do the computation and process it through your own work so you can follow through. We're not done yet. So just like before, now we don't touch anymore. So R3, don't use it anymore from this point on, because you don't want to affect again the zeros created above this leading one. You're going to use row 2 to produce again the only remaining 0 to be produced, right? Because to get to the reduced row echelon form, you want to have zeros above leading ones. First column satisfies the property. The last column satisfies the property, right? I have only zeros above leading ones. The only thing left to be done is to do a 0 above leading one for the second row. And the only way to do this is to change row 1 with row 2 times 2 and add it to row 1. Yeah, 1 times 2 minus 2 will make it 0. And again, from bottom up, copy the last row. Second row again stays the same, and only the row 1 will change. 0 times 2 plus 1 remains 1. 1 times 2 minus 2 is 0. 0 times 2 plus 0 is 0. 1 times 2 plus 0 is 2. So this is a far more efficient, I mean, not efficient, the format of the matrix is much simpler than before. Because now if you want to write the equations, notice the equations give you already the variables. So if you want to write the system that you get, that's going to be x plus 1 times x plus 0 times y plus 0 times z equals 2. That doesn't fit here. Sorry about that. Let me write it here. So basically the system is 1 times x plus 0 times y plus 0 times z equals 2. 0 times x plus 1 times y, 0 times z equals 1. 0x plus 0y plus 1z equals 1. You don't need to write it that expanded. I mean, you could see right away with little practice that the equations that are left give you actually directly the solution of the system, 2, 1, 1. If your goal is just to solve a linear system, it's not really strictly necessary to move to reduced row echelon form. So unless required, and in some cases you are actually required to do that, but unless required, in solving a linear system, the reduced row echelon form is optional. I would say that because whatever the time you save for not doing these substitutions that we needed to do from the reduced echelon form, so whatever the time you save by not doing this, you're going to spend by doing the extra eliminations. On the other hand, with a little practice, and if you're comfortable with row operations, these extra eliminations that you need to move from row echelon form to reduced row echelon form, this part is usually not that difficult because you already have plenty zeros. And again, like I said, if you know how to do row operations comfortably, this shouldn't be an issue. But for now, just for practice, I would advise you to actually go for the reduced row echelon form just to practice with these mechanics. And also because in some other applications, you will actually need to produce these matrices in the reduced row echelon form. We will continue with some extra examples, and I'm going to comment on some, this time around, how this process looks like if you have the number of equations and unknown not equal to each other. Because so far we had either 2x2 systems or 3x3 systems. And so let's see how the algorithm looks like if you have an arbitrary number of equations and unknowns. So stay tuned. All right, so let's deal now with equations in M unknowns and M equations and N unknowns. So in which the number of equations and unknowns is not the same necessarily. The first thing to do, so I wrote already, take a moment, pause and write these examples. Let's label them by A, B, C, D. So before we move on and see how we solve each of these systems, let's see if we recognize which one is in the row echelon form, reduced row echelon form, or neither of the two. So pause for a moment and see if you can find the answer, and then we will figure out the solution in each case. All right, so assuming you try to do that, the answer is the following, and we can comment on this already. The first one is in the row echelon form. Okay, so let's check quickly. Leading ones, those are the leftmost non-zero entries on each row. Those should be 1. Okay, so these are the leading ones that I just circled here. The second characteristic is that below each leading one, there should be 0 entries. There are only 2 rows, so the only 0 requirement is over here. 0 below the first leading one, and that's it. This is a augmented matrix in the row echelon form. Okay, how do you solve the system? Because in this case, you may wonder, okay, I mean, I have 3 variables. If I were to write the system, this corresponds to a system of 3 variables and 2 equations, or 3 unknowns and 3 equations. Excuse me, 3 unknowns and 2 equations. What do you solve for? Well, as a rule of thumb, or as if you want, a standardization of the algorithm, we always solve for the unknowns corresponding to the leading ones. In this case, x and y. And the other variables, if any, there will be arbitrary. So this is a case in which you will have infinitely many solutions. So how do we solve them? From bottom up, just like before. So from the last equation, I get that y is 3 minus z. That constitutes the solution for y. Plug it into the first equation. Let's do some algebra here. 6 minus 2z plus 3z equals 4. Move it to the right. 4 minus z minus 6. That's minus z minus 2. So x is minus 2 minus z, or minus 2 minus z, whichever you prefer. And z is arbitrary. So this is a consistent system with infinitely many solutions. Whenever you have basically fewer leading ones than unknowns, you typically end up with this situation. Let me double check quickly. 3 minus z, let's see, 4 minus 2. So x plus 2 times 3 minus z plus 3z, 6 minus 2z, all good, 4 minus 6. Okay. So you always solve for the leading ones, as I said before. All right. Notice carefully on the system B. So let's make another B column here. This basically is neither in the row echelon form nor reduced row echelon form. So let's see which part of the system doesn't fit the description. Well, the leading one, so this is the first leading one, but there are no, there should be zeros before leading ones. So the problem is with the 1 below the first leading one. That should be 0. So basically, if you are in this configuration, the first thing to do is to basically replace row 2 by minus 1 times row 1 plus row 2. And if one does that, let's see, we have minus 1 plus 1, 0, minus 2, minus 1 times 2 plus 0 is minus 2, minus 3 plus 1 is minus 2, minus 4 plus 3 is minus 1, and then 0, 0, 1, and 2. Now, you're still not done because the last thing to do here is to create a leading one in place of this minus 2. So remember that the leading ones are the first non-zero entries on each row. So this became minus 2 because when I created the 0 below the first leading one, I automatically placed minus 2 here, right? So from 2 times minus 1 plus 0. So here we will follow up by row 2 divided by minus 2. There might be some noise, background noise, sorry about that. So 0, 1, 1, 1 over 2, 0, 0, 1, and 2. This will be in row echelon form. I'm not going to solve it for now because I want to move on to the other 2 examples. You will have to deal with fractions in this case, but you can proceed and solve the system, right? I mean, the equations of the system are x plus 2y plus 3z equals 4, y plus z equals 1 over 2, and z equals 2. So you can do it as an exercise, just plug in back z and y and find x, y, and z. But again, the emphasis that I want to make on this example is that it is neither in row REF nor RREF, right? So it's basically somewhere in the middle of the process if you want. So make sure you don't confuse intermediate steps to the reduced echelon form, row echelon form, or reduced row echelon form. The example C, this one is again in REF form. It's actually similar to the first one. So let's write again the equations. So x plus y plus 3z equals 5, y plus z equals 6. Do it as an exercise yourself. you will end up again with infinitely many solutions. Because z will be arbitrary. You have two leading variables, x and y, and one arbitrary variable z. I want to comment on part D a little bit here, because this is sometimes confusing to students when they have this situation with unequal number of equations and unknowns. If you look carefully and follow the definition, you should have recognized that this is in reduced row echelon form. People are confused sometimes because in most of the examples, reduced row echelon form contains column like this, 1, 0, 0, 0, 1, 0, 0, 0, 1, and so on. So in between, it seems strange that you will have unusual columns like these 2, 0 over there. But remember, the only requirement is that the leading ones, which I emphasize right now in a square, they should be shifted to the right as you move from top to bottom. Nothing says that the shift should be one position only, like in the previous examples. So the shift could be two positions. If you look carefully, this perfectly satisfies the reduced row echelon form definition. Let's go again over the requirements. First non-zero entry on each row is 1. Checked. Zeros below each leading one. 0, nothing below the second leading one. Zeros above leading ones, nothing above the first leading one, 0 above the second leading one, which happens to be on the third column. So column 2 is not a leading column. And the leading variables are x and z. So they don't have to be in order. They don't have to be x and y in that order. 1, 0, 0, 1, those are the leading columns. In between, you could have other types of columns. As long as it follows the definition of the reduced row echelon form, then you're good to go. Nothing really fancy or special in solving the system, except don't forget to remember what are the variables corresponding to the leading ones. When I write the equation of the system, that's x plus 2y plus 0 times z equals 3. And 0 times x plus 0 times y plus 1 times z equals 7. I solve for the leading variables. That means z equals 7. And there's nothing to plug in, z on the top, because it's multiplied by 0. And I solve for x in the first equation, and I'm done. Y is again arbitrary, because it's not the leading variable. And again, we have infinitely many solutions. With that being said, I'm going to go over 2 more examples from the beginning to the end with the system, and that'll be it. All right, so let's start with a system, and in all cases, we're going to proceed until we figure out the reduced row echelon form and then solve it. This is the first one that I go through now. It's a system of 2 unknowns and 3 equations. So the augmented matrix is 6, 1, and 8, 1, minus 3, and minus 5, 2, 1, and 2. Let's try to be more efficient. We already have a 1 in the first position here. We're going to do an interchange. Row 1 with row 2 to place it in the first position. Row 1 will become the old row 2 times minus 6 plus row 1 to make a 0 in that place. And then row 3 will become minus 2 times row 2 plus row 3. Minus 2 times row 2 plus row 3, the old row 3. By the way, once you are comfortable with these operations, you don't need to specify them all the time like I do it here. Just do that while you're still shaky on these mechanics. But once you are comfortable with the row operations, you could do them a little bit faster. So 1 times minus 6 plus 6 is 0. Let's see, minus 6 minus 3 plus 1, that makes it 19. Minus 6 minus 5, that's 30. plus 8 is 38. And then minus 2 times 1 plus 2 is 0. Minus 3 minus 2, that's 6, plus 1 makes it 7. Minus 2 minus 5, 10, plus 2, that's 12. I'm done with the first row and the zeros below it. Let's do the second row. I'm kind of lucky because I don't have fractions here, because to produce the leading one, now I have to divide row 2 by 19. So 1 over 19 times row 2. That's the easiest way to produce the leading one on that position. So 0, 1, 2, and then 0, 7, 12. Okay, I produced the first leading ones. Now let's produce 0 below the second leading one. So at this point, I'm not touching the first row anymore. Second row again stays the same. And all I'm doing now is minus 7 times row 2 plus row 3, which will replace row 3. So that makes it 0, 0. Minus 7 times 2, that's minus 14. Plus 12, that's minus 2. So notice that the leading one on the third column happens to be to the right of the equal sign. In this case, actually, I'm not going to move on to the reduced row echelon form. There's no point in doing that. So this will be the REF form, because already we noticed that the system is inconsistent. So there's no point in basically continuing solving the system if you realize you have no solutions. Why? Because the last equation essentially tells you that 0 equals 1. So if you write the last equation, that's clearly not possible. So it's a waste of time to continue with the more simpler reduced row echelon form. All right, so let's go over another example. Actually, before I move on with another example, I should point out that it's not always the case that if you have more equations than unknowns, you always have inconsistent system, right? I mean, because sometimes people may think that it's overdetermined, right? I mean, you have more equations than unknowns. You could end up with a third equation that is compatible with the first. So for example, let's say you have, let's actually go over this extra example, which I didn't plan, right? But let's say you had, let's see, 6x plus y equals 8, x minus 3y equals minus 5. And what if the last equation was 7x minus 2y equals 3? If you look carefully, all I did I added the first two equations. I mean, which means the third equation doesn't bring you anything new, and this will cause you actually a 0 row. And the system will be actually consistent if you follow through with the same approach. So if you were to do, again, the augmented matrix, just like we did before, I'm going to do it a little bit faster now, just to see the effect. The first steps are really the same as before. Interchange, make zeros. So minus 6 plus 6, 0. This is 19. Let's see, 38 as well. That doesn't change. And now pay attention how the last row changes. I have to multiply again by minus 7 this time and add. So the last operation here is minus 7 times row 2 plus row 3. Minus 7 times minus 3, that's 21. 21 minus 2, that is 19. Minus 7 minus 5, that's 35, plus 3 is 38. Notice already that the last two rows are the same. Divide by 19. Let's divide by 19 both of them. And when the time comes to produce the 0 below the second leading one, you will happen to have a completely 0 row. So this will be a consistent system, because when you write it down, you will have x minus 3y equals minus 5. Y equals 2, the last equation is eliminated, right? It was a combination of the first two. And then you can just plug it back into the first equation, and then that's x equals 1. 1 and 2. So don't assume whether you have a consistent or inconsistent system just because you make some assumptions regarding the number of equations and unknowns. You could have all possibilities, well, almost all possibilities essentially. There's more to that, if you go through linear algebra, but for now, go through the algorithm and don't assume anything until you actually see what the end result is. I mean, in terms of whether it's consistent, inconsistent, or whether you have unique solutions or infinitely many solutions. Let's do one more example, and I think that's enough for this lesson. So suppose the system is 2x plus 2y plus z equals 5, x plus y equals 2. Be very careful when you write the augmented matrix to place 0 coefficients for any missing variable. So notice the second row is 1, 1, and 0 in that order because there's no z on the second equation. We do an interchange. So interchange row 1 with row 2 because we already have 1 on the left side on that row. And the only thing left to do is to make 0 below it, which is to say you're going to replace row 1 before the interchange, of course, row 1 with minus 2, row 2 plus row 1, and place it in the second position. So then minus 2 times 1 plus 2 is 0, minus 2 times 1 plus 2 is 0, 0 times minus 2 plus 1 is 1, minus 2 times 2 plus 5 makes it 1. And notice this is already in reduced row echelon form. Again, pay close attention and don't get confused. The leading columns are 1 and 3. Not the second one, which just by coincidence happens to be the same as the first one. That's just a coincidence. The second entry here could be any number. Second entry on the first row could be really any number over there. The columns, the leading ones, are the leftmost non-zero entries on each row. 1, 0, and then 1, 0 with 0 above it. When you write the equations of the system now, we have x plus y equals 2, z equals 1. And again, we solve for the leading variables, the variables corresponding to the leading ones. And because y is not a leading variable, it remains arbitrary, and we have infinitely many solutions. When we say infinitely many solutions, that basically refers to x, because z happens to be precisely 1, but because y is variable, you still have infinitely many solutions because we have infinitely many possibilities for x. Basically, a unique solution happens when each variable, so basically a unique solution is when you have a leading one for each unknown. But you don't have to memorize this kind of fact. This is more of the interest of linear algebra, where people study in more depth the linear systems, among other things. Just make sure you understand the algorithm and how it works. And we'll talk more on this, hopefully during online office hours after you do the homework. I'll see you next time.